We're talking about the Hardy-Weinberg Principle today, and this theorem or postulate describes a hypothetical population that is not undergoing evolution, but only if there are no mutations, no random mating, no natural selection going on, extremely large population size, and no gene flow. So if these five things are occurring, you could be in a scenario where your population is not undergoing any evolution. That is very, very difficult to have these five things going on, especially the mutations and the random mating and the gene flow. But if you can, you could have possible this equilibrium. Now, equilibrium means there's no change in the number or frequency of certain alleles. See, the idea that evolution is occurring is important to understand, but this evolution can be looked at on the micro scale. We talk about the Hardy-Weinberg principle, we're talking about the micro evolution, the evolution of, let's say, certain alleles. So we're looking on a chromosome of one locus, or one place on the chromosome, and we're talking about the number of dominant or recessive alleles for that one gene, okay? And that's what we're looking at here. So again, this is a hypothetical scenario, but one that's very important because we have to have a baseline to know if evolution is occurring on this micro scale in a population. We have to know where our baseline would be to compare to. So it's very important. And there are certain scenarios where we can use these equations to get a good piece of information. And the PKU disorder, that recessive disorder we talked about, is one place we can do that. So where are we? Well, we left off talking about if I had a dominant allele, K, and a recessive allele, K, and we knew their frequency in population. Meaning what? Meaning 80% of all the alleles in the population that we're dealing with for that just one little place, one gene, or that one allele, 80%. And Q had to be 20%. Why? Because, well, P plus Q equals 1. It's the addition rule, because if you're either going to be either going to be a dominant allele or the recessive allele for that one trait that we're looking on that's basically controlled by one gene. Okay, so that's what we did here. Now, the little p represents the frequency of all those alleles. Some of those alleles will be in what? Heterozygous individuals, and some will be in recessive individuals, and some will be in homozygous dominant individuals. So we talk about alleles, you have to remember that we're dealing with either, where are the recessive ones? Well, they're in the, of course, there's two in the people that have the recessive trait, and there's one that are heterozygous and none. So that's where we're getting this from. And because you either have a K or a large dominant or recessive, one or the other, that's why we add. But now, what we're going to do is from the P values or Q values, right? The Q values would represent all of these Ks, okay? In this case, I have 50%, but we're just making it up. And the Q represents all of the recessive ones. But that doesn't give me individuals. So we do a cross. So if you remember, I'm crossing my dominant gene with the recessive. Those are the two possibilities in my population, with another parent, okay, that is dominant recessive. Those are the two possibilities of gametes in that population, right? That's all you have. And you get this cross. And notice I get homozygous dominant. And you notice it's what it is. It's 0.8 times 0.8, or P squared. Okay? And of course, when my little k and little k come, I get 0.2 squared, which is Q squared. Very interesting. And if you notice here, K, big K, little k, you get 0.8 times 0.2, which is PQ. And you have two forms of PQ. And that's where this comes from. So when we took and multiplied PQ times PQ, we get this formula. We have our PQ, which is right here. We're taking the what? To get the individuals that are homozygous dominant, we would square the what? The P value. To get the individuals that are homozygous recessive, we square the Q value. And the rest of the individuals that are heterozygous, we put here, notice the 2 here, because there's 2 of them. And it would have to equal 1, and we showed that. Now, to get the absolute frequencies of these genotypes of the people, see, we're moving from frequency of what? Of the alleles to frequency of the genotypes of individuals. That's important here, very important. We're going from the total number of alleles in the population to actually what? People. That's really important you grab that. Okay, so to find the total people, I just do my math. Well, homozygous dominant, well, my friends, isn't that p squared? So that's going to be equal to 0.80 squared. And of course, that equals 0.64. Now, what does that mean? 64% of all my individuals in my population must be what? Homozygous dominant if the p-value, okay, the frequency of the dominant gene is what is 0.80. So it's interesting that we can get that value there. Now, homozygous or heterozygous, we have, remember, 2pq. So we have 2 times 0.80 times 0.20. Let's put that in our calculators. 2 times 0.80 times 0.20. And I get 0.32. And then kk is q squared. And that's 0.20, it's a point there, squared. That's 0.04. Notice when I add them up, all right, they will all equal to 1. Interesting. Shouldn't they add up to 1? Yes, they do. Okay. Now, so let's take some real data. Okay, that was just hypothetical data to make some learning. So when we talk about the PKU occurrence of that disorder, which is again a recessive disorder. Okay, we know currently that the disorder occurs when you get, of course, both recessive genes, both alleles that are broken, that can't make the enzyme or the protein to break down this certain amino acid. We know that currently it's 1 per 10,000 births. So to find a frequency of this type of genotype, I do 1 divided by 10,000, and I get this value. Now, what does it mean? This is the frequency of these individuals. So Q squared, okay, is equal to 0.0001. This is Q squared, right? Talk about people. The actual genotypes are from this equation. And this equation came from the mating or putting together of the gametes, right? So the P's and Q's are the total frequencies of the entire alleles in the population. This is the frequencies of the entire phenotypes, okay? Or genotypes of the people. Okay, now let's get back to where we were. So to find the Q, or the frequency of just the Q allele, the recessive gene, or the recessive trait allele, we take the square root of Q squared, because the square root of Q squared is Q. So since Q squared is equal to 0.0001, we take the square root of it, and we get 0.01. What does that equal? Don't get lost. It's equal to my Q, which is what? The frequency of all of the recessive in our population. All right. Now, what would be P then? Well, wait a minute. If I know that P plus Q equals 1, and I just found out my Q is 0.01, what must be P? What plus 0.01 is 1? Or if you want to do algebra, P is equal to 1 minus Q. And what should you get there? You're going to get 0.99. Right? If P plus Q equals 1, and I know that my Q is 0.01, 1 minus 0.01 is equal to 0.99. So my frequency of the normal alleles of the entire population is 0.99. What's the frequency of carriers? Okay, well, if I know it's 2PQ, which is really this genotype, I do 2 times my P. What is my P? In this case, it's 0.99 times my Q, which is 0.01. Let's put that in our calculator and go ahead and go for it. 2 times 0.99 times 0.01, and I get 0.0198. Now I convert that to a percentage, right? I'm going to times that by 100, so that would be 1.98%. And this is approximately what? Round that off, and you get approximately 2% of the U.S. population is a carrier that has at least one recessive gene that carries the trait. Okay? And we got all of that, we got all of that from starting from a what? A rate of disorder per births. So we can speak to that and you can see how powerful that is. Okay, hope that helped to see how easy this is. The concept is a little strange at best, and again, you got a little lowercase letters to follow. And don't forget, in your reference table, you have both of these. Well, you have the formula to look at. Let me show you. Yeah, so there it is, right in your first page of your reference table. You have underneath the chi-squared that we did there and the laws of probability. We have the Hardy-Weinberg, and look what it gives you, some nice understanding. The little p by itself, these are individuals. These are the frequency of the individuals who have the two. This is the recessive, the homozygous dominant. This is the carrier or the heterozygous. These are the people, the frequency of the people. So the little p by itself is the frequency of all the dominant alleles. This is all the recessive alleles. So these are all the alleles, and these are the people. To keep that straight, it makes this much, much easier to understand. Hope that helped.